Hi guys, so today I want to talk about horizontal projectiles, and we're going to do that using your basketball physics lab from Pivot. So if I come over to Pivot, okay, you had this video here of this boy shooting a basketball, okay. When he shoots the basketball, the total video is going to give us this shape that almost looks like a parabola. Okay, technically it is a parabola, it's just not finishing down back to the point where it started. We will do full parabolas in our next discussion, but for today we're doing something called a horizontal projectile. So in a horizontal projectile, it either needs to end or begin with no velocity in the y direction. So I'm going to start from this first basketball, go up here until it reaches the peak of the parabola, because at this peak of the parabola, it is moving to the right. It is moving horizontally until it starts to go down, okay? So I want to look at just the motion from this basketball up to this basketball, okay? So here at this basketball, the velocity is moving in the x direction only, so that means that the velocity in the y direction is going to be 0, i.e. making it a horizontal projectile. So from here, all of these basketballs show a motion that's moving up and to the right, and then when we reach this peak, just to the right, and then these would all be down and to the right. And we'll focus on that second half of the parabola next time. So when we look at our graphs that you made, I'm going to draw them just for the first half of that motion until we hit the peak. So you should have gotten a little bit more than what we're about to see because you did more of the motion, okay? I'm going to look at our position in the x direction versus time. And then I'm going to look at our position in the y direction versus time. Remember that I'm using x for moving in the x direction and y for moving in the y direction. And now that we've done forces, you've been able to see that one object can move differently in the x direction than it does in the y direction. So that's going to lead us into this basketball moving in this parabola shape, meaning that it's moving in both directions at the same time, but those motions don't have to be the same. So this x versus time, if I just go from the first basketball to the peak, should give us a straight line. And then this y, if I go from the first basketball to the peak, should end up looking like the first half of our parabola. So here, if I look at our equation for our first graph, I don't know why I wrote y. Hold on. Oh, I know why I wrote y, because I'm going to do y is equal to slope times x plus b. So I'm just putting it into the normal slope equation form. Okay. My y-axis is our x positions. Our slope, if you remember from our kinematics, our first kinematics unit should be the velocity because the slope is a meter divided by a second. So the slope of a displacement time graph or a position time graph is going to give us the velocity. Our x is our time, and then if you have an intercept, it would be along this position axis, so it would tell us our initial position. So the equation for this line gives us the kinematic equation delta x is equal to vt. So if I look at this graph, I asked you to find the slope, the numerical value for the slope. So the slope is going to tell us our velocity in the x direction, and that value should be a constant number because our line is straight. So if our velocity is constant in the x direction, that means our acceleration in the x direction should be equal to 0. All right. So then if I come over to our y direction versus time graph, this is half of a parabola, and a parabola best fit equation is for a is the quadratic equation. So we get y is equal to bt plus a t squared plus c. Okay, so our y is our y position. Our b is going to end up being our velocity in the y direction times time, plus a, which will be 1/2 a t squared, plus c, which would be our y initial. And I know that because just like the equation for this x direction graph, the equation for this y direction graph is also a kinematic equation. So this is our delta y is equal to vy t plus 1/2 at squared. So these graphs are giving us two of the kinematic equations. Okay. Now, if you remember back to this equation, this is not just the velocity in the y direction because I have an acceleration, so that velocity is going to change. This term was our initial velocity. So this is going to tell us our initial velocity in the y. So then if I compare my fit equation with the kinematic equation that it is, then I know that B tells us our initial velocity in the y, and that's some singular constant number. Okay, and then my A parameter tells me 1/2 of my acceleration. So my A parameter, my acceleration in the y direction should be our negative 9.8 or our negative 10. It should be the acceleration due to gravity, and I will show you why in a second. But this should be something like 1/2 times negative 9.8. So hopefully your A parameter came out to be something kind of like negative 4.5. Okay, so that means that our acceleration in the y direction should be our acceleration due to gravity of negative 9.8 meters per second squared. All right, so the reason why that acceleration is a negative 9.8 is because once the ball leaves the hand, it is in free fall. And when it's in free fall, that means that the only force acting on it is the force of gravity. So yeah, the boy pushes it, but I'm not looking at it when he's pushing it with his hand. I'm looking at it after it leaves the hand. So after it leaves the hand, the only force acting on it is the force of gravity. So that means if I look at the sum of the forces in the x direction, there are none. That's not a thing, okay? So if there's no forces, that means there is no acceleration, which is what we found in our x direction graph up here when we said the acceleration in the x direction is 0 because the slope is the velocity in the x direction and it's a constant value. So our velocity is not changing. So then if I look at the sum of the forces in the y direction, it is unbalanced. I only have one force, so it cannot be an equilibrium. So that needs to be equal to ma. And then in the y direction, I only have the force of gravity. So the force of gravity is equal to ma, which makes mg equal to ma. Those m's would cancel. So our acceleration in the y direction is equal to g, which is our acceleration due to gravity. So when I'm looking at these motions, the x direction is a constant motion while the y direction is in free fall. So when I look at my kinematic equations that we're about to go through, I have to treat them separately. I have to use the kinematics in the x direction separate from the kinematics in the y direction because my motions are two different things. So let's remind ourselves of these kinematic equations. All right, so I'm going to start with the x direction because it's much simpler. The first equation I want to look at, we had delta x is equal to v naught t. I'm going to make it v naught x because this is the x direction, plus 1/2 acceleration in the x direction times t squared. But acceleration in the x direction is 0. So delta x is just going to be equal to v naught xt, which was the equation of our line above. So I can use that guy in the x direction, but that's actually going to be the only kinematic equation that works in the x direction because that acceleration is 0. So if we remind ourselves of the other ones, we would have v final in the x direction is equal to v initial in the x direction plus acceleration in the x direction times time. But again, acceleration in the x direction is 0. So this equation just tells me that the final velocity in the x is equal to the initial velocity in the x, which is a true statement if acceleration is 0, but it's not an equation that I can use to solve for anything. And the same thing happens with our third kinematic equation. Scrolled down a little too far. So our third kinematic equation that we used was v final x squared is equal to v initial x squared plus 2ax delta x, where ax is 0. So this one again just tells me that the final velocity squared this time is equal to the initial velocity squared, which is the same business that we just talked about. So both of these equations can't be used to solve for anything in the x direction because our acceleration is 0. But the y direction is a different case because the y direction we do have an acceleration. So this equation would be delta y is equal to v naught y t, okay? Our acceleration is negative g, so remember I pull out my negative, do a 1/2 g t squared because g is negative and it's our negative 10 or a negative 9.8. I could use that one to solve for something in the y direction. Our second equation is our v final y is equal to v initial y, again, negative g t squared. So I'm putting the negative because g is negative. Oh, I don't know why I put a squared. Okay, and then our final equation would be v final y squared is equal to v initial y squared minus 2a, oh, I put a instead of g, sorry, I'm a little distracted, g delta, I did it again, delta y. Sorry guys, delta y. All right, I think we're on the right track now. So these all three kinematic equations will work in the y direction because I have an acceleration. So these kinematic equations that I'm looking at are the same kinematic equations from the first unit. However, we are splitting them up into the x and the y direction. So the only thing I'm changing is I'm adding little descriptors here of y, and x over here to make sure that I keep them straight. All right, so using this idea, I want to look at another type of horizontal projectile. So this basketball horizontal projectile, we went from down here and we ended with a velocity in the y direction that would be 0. I want to look at one where I'm going to start with a y velocity being equal to 0. And the way I'm going to do that is I'm going to look at something being launched off of a cliff. That's a pretty normal example. However, I'm going to pause here because I'm about to run out of time. So pause, please, go to part 2.